Welcome back to our lesson 1 in mechanical waves. Let's now proceed to the sections 5, 6, and 7 of this mechanical waves. First, section 1.5, wave interference, boundary conditions, and superposition. Up to this point, we've been discussing waves that propagate continuously in the same direction. But when a wave strikes the boundaries of its medium, all or part of the wave is reflected. For example, when you yell at a building wall or a cliff face some distance away, the sound wave is reflected from the rigid surface and you hear an echo. When you flip the end of a rope, whose far end is tied to a rigid support, a pulse travels the length of the rope and is reflected back to you. In both cases, the initial and reflected waves overlap in the same region of the medium. This overlapping of waves is called interference. Now, what happens when a wave pulse or a sinusoidal wave arrives at the end of the string? If the end is fastened to a rigid support, it is a fixed end that cannot move. The arriving wave exerts a force on the support. The reaction to this force exerted by the support on the string kicks back on the string and sets off a reflected pulse or wave traveling in the reverse direction. The opposite situation from an end that is held stationary is a free end, one that is perfectly free to move in the direction perpendicular to the end of the string. The conditions at the end of the string, such as a rigid support or complete absence of transverse force, are called boundary conditions. For the principle of superposition, combining the displacement of these separate pulses at each point to obtain the actual displacement is an example of the principle of superposition. When two waves overlap like in the figure, the actual displacement of any point on the string at any time is obtained by adding the displacement to the point would have been if only the first wave were present and the displacement it would have if only the second wave were present. The principle of superposition is of central importance in all types of waves. When a friend talks to you while you are listening to music, you can distinguish the sound of speech and the sound of music from each other. This is precisely because the total sound wave reaching your ears is the algebraic sum of the wave produced by your friend's voice and the wave produced by the speakers of your stereo. If two waves did not combine in the simple linear way, the sound you would hear in the situation would be a hopeless jumble. So, in short, superposition also applies to electromagnetic waves such as light and many other types of waves. Now, let's look on this slide. The figure shows a string that is fixed at its left end. Its right end is moved up and down in simple harmonic motion to produce a wave that travels to the left. The wave reflected from the fixed end travels to the right. The resulting motion when the two waves combine no longer looks like two waves traveling in opposite directions. The string appears to be subdivided into a number of segments, as in these examples. For A, the string is 1/2 wavelength long. And for the B, the string is 1 wavelength long. For the C, the string is 1.5 wavelength long. When we say wavelength, it is a combination of these two. So this is a 1/2 wavelength long. This is a 1 wavelength long. And this is a 1.5 wavelength long. And this is 2 wavelength long. 1 and 2. In this figure, letter E shows instantaneous shapes of the string in B. This is a string representing this letter B. The N represents the nodes. There is a point at which the string never moves. So this is a node, and a node. When we say A, that is an antinode. It is a point at which the amplitude of string motion is greatest. So dito sa antinode, dyan nagkakaroon ng highest amplitude. So when we say node, it is a part of the string that does not move, and when we say antinodes, that is the highest amplitude of the string it can reach. In a wave that travels along the string, the amplitude is constant and the wave pattern moves with a speed equal to the wave speed. So here instead, the wave pattern remains in the same position along the string and its amplitude fluctuates. There are particular points called nodes, labeled N, in the figure that never move at all. Midway between the nodes are points called antinodes, or labeled A, where the amplitude of motion is greatest. Because the wave pattern doesn't appear to be moving in either direction along the string, it is called a standing waves. Okay? Next, normal modes of a string. When we describe standing waves on a string, rigidly held at one end as in this figure, we made no assumptions about the length of the string or about what was happening at the other end. Let's now consider a string of a definite length L, rigidly held at both ends. Such strings are found in many musical instruments, including pianos, violins, and guitars. When a guitar string is plucked, a wave is produced in the string. This wave is reflected and re-reflected from the ends of the string, making a standing wave. This standing wave on the string, in turn, produces a sound wave in the air, with a frequency determined by the properties of the string. This is what makes a stringed instrument so useful in making music. If a string with length L is fixed at both ends, a standing wave can exist, thus giving the equation 1.7, or in general, some integer n of half wavelengths lambda. Equation 1.8, on the other hand, is called the fundamental frequency of string fixed at both ends. And equation 1.9 is the standing wave frequencies called harmonics, and the series is called a harmonic series. Musicians sometimes call F2, F3, and so on overtones. F2 is the second harmonic or the first overtone. F3 is the third harmonic or the second overtone, and so on. So, in this figure, when we say N is 1, and that is F1, it has a F1 harmonic or first harmonic. And when we say F2, the N is 2, it has a second harmonic and has a first overtone. So second harmonic, first overtone. If N is 3, it has 3 harmonic and has 2 overtone. And when we say 4, it has 4 harmonic, fourth harmonic, and has third overtone. Now, let's proceed to the standing waves and string instruments. This equation 1.10 is also the fundamental frequency of the sound wave created in the surrounding air by the vibrating string. Familiar musical instruments shows how F1 depends on the properties of the string. Increasing the tension F increases the wave speed V, and thus increases the frequency and the pitch. All string instruments are tuned to the correct frequencies By varying the tension, you tighten the string and to raise the pitch. Finally, increasing the mass per unit length decreases the wave speed and thus the frequency. The lower notes on a steel guitar are produced by thicker strings, and one reason for winding the bass string of a piano with wire is to obtain the desired low frequency from a relatively short string. Let's proceed to the learning activity 1.4 titled A Giant Bass Viol. In an attempt to get your name in Guinness World Records, you build a bass viol with string of length 5 meter between fixed points. One string with linear mass density 40 gram per meter is tuned to a 20 Hz fundamental frequency. That is the lowest frequency that the human ear can hear. Calculate A. The tension of the string, B. The frequency and wavelength of the string of the second harmonic, and C. The frequency and wavelength of the string of the second overtone. For the solution, identify and set up. In part A, the target variable is string tension F, and we'll use equation 1.10, which relates to F, the unknown values, with fundamental frequency 20 Hz. And this was given in the problem. The length of the string is also given, 5 meter. And the linear mass density is also given, 40 gram per meter. And in parts B and C, the target variables are the frequency and wavelength of a given harmonic and given overtone. We determine these from the given length of the string and the fundamental frequencies using equation 1.7b and 1.9. So by doing execution A, we solve equation 1.10 for F. Now F is equals to 4 mu L squared F1 squared. And when we put in the values for the linear mass density mu, the length of the string, and the fundamental frequency of the string, we can get a 1,600 Newton force or tension force or 360 pound force. For letter B, from equations 1.9 and 1.7b, the frequency and wavelength of the second harmonic, when we say second harmonic, it means n is equals to 2. And it is equals to F2 equals 2. This is the n and this is the F1. F1 is 20 Hertz. Okay, so 2 times 20 Hertz is equals to 40 Hertz. Now, the wavelength of the second harmonic is equals to 2L over 2. And the L is given 5 meters. So, that is cancelled. So, the wavelength of the second harmonic is equals to 5 meters. The second overtone is the second tone above the fundamental. And that is N equals 3. Magkaiba si harmonic and si tone. Okay, when we say second overtone, it has a third harmonic. Okay, so si N is 3. Its frequency and wavelengths are the same with this procedure. You get F3 equals 60 Hz and the wavelength for the second overtone or the third harmonic is equals to 3.33 meters. Evaluate. The string tension in a real bass viol is typically a few hundred newtons. The tension in part A is a bit higher than that. And wavelengths in part B and C are equal to the length of the string and 2/3 the length of the string respectively. Now for the next learning activity 1.5 entitled From Waves on a String to Sound Waves in Air. What are the frequency and wavelength of the sound waves produced in the air when the string in learning activity 1.4 is vibrating at its fundamental frequency. The speed of sound in air at 20 degrees Celsius is 344 meters per second. Solution. Identify and set up. Our target variables are the frequency and the wavelengths for the sound wave produced by the vast field string. The frequency of the sound wave is the same as the fundamental frequency F1 of the standing wave because the string forces the surrounding air to vibrate at the same frequency. So, frequency of the sound wave is just equals to the fundamental frequency F1. The wavelength of the sound wave is lambda 1 of sound equals to speed of sound over the F1. This formula is given as a previous nating lesson, sections 1 to 4. So, execution. We have frequency equals to F1 equals to 20 Hertz. So, the wavelength of the sound equals the speed of the sound over the frequency. And speed of the sound is 344 meters per second over 20 Hertz. That is equals to 17.2 meter wavelength. And that ends the topic for our lesson 1 mechanical waves that has sections 1, 2, 3, 4, 5, 6, and 7. Up next is the learning evaluation that I will provide to you in our LMS Moodle.